We can build machines that are faster than us, or stronger than us, or more precise than us. But can we ever build machines that are more intelligent than us? I believe the answer to that question is yes. And that's why I'm so excited about artificial intelligence. And I think understanding AI is one of the most important skills to have at this time. We have already seen successful applications of AI in search engines, chatbots, art, robotics, and many other fields. These are all the results of progress made over the past couple of decades in the field of AI. But there's also a whole lot yet left to be discovered and invented. So whether you just want to have a basic understanding of AI or you want to actually use AI to solve new problems, this video is for you. I will talk about some fundamental ideas that pretty much every modern AI system uses, and I will show you how to implement these ideas in Python. So let's get started. The word AI nowadays has become synonymous with machine learning. While there are non-ML approaches to AI, the field of AI has been dominated by machine learning for many years. Machine learning makes it possible to program our computers in an entirely new way. Traditionally, the main way computer programs were designed was by human experts writing down the steps to the solution of a given problem in very specific and easy to follow instructions. So this approach works great if you know the exact solution to the problem you're trying to solve. And it turns out there are a ton of things we know exactly how to do. However, there are some problems even our smartest scientists don't know how to solve with this traditional way of programming. Take, for example, recognizing if a given image is a photo of a cat or a dog. That rather simple question turns out to be impossible to solve just by writing down the instructions for the computer. That's because no one really can explain how they recognize a cat in a way that a computer can understand. We have learned to identify cats by examples, not by a detailed description of a cat. And that's very similar to how machine learning works. Machine learning is a new approach to programming based on data. Let's try to understand how it works with a simple example. Say we want to predict how much a house would sell for in a hypothetical town. Assume we don't know anything about real estate, but we have access to records of recently sold houses, and we want to build a model of house prices. For a given house I, the model would take the house attributes like location, size, and the number of rooms as input and produce a predicted price as output. Okay, now before trying to even suggest a solution to this problem, it's a good practice to start with a way of evaluating our solution. We can, for example, say that our prediction is good if the absolute difference between our predicted price and the real house price is low. This function is also commonly referred to as the loss function. Now, of course, we want to make this prediction on the houses that we don't know the price of. So, to fairly measure that, let's split our data into two parts. One part of data we're allowed to look at when we are trying to build our house price model. We call this the training set, and the other part we keep hidden from ourselves and only use for evaluating the performance of the model. And we call that the test set. This way, if we can build a model that achieves low errors on the test set, we can be more confident that the model would perform well on any new house. Now, if I give you the training set and ask you what's the price of houses in this town, you might say about $450,000. You actually just created a model, the simplest of models, that is just a constant. The constant model has the form of f equals w. This model also can be seen as a neural network with just one parameter. The parameters of neural network models are commonly referred to as weights. So is this a good model? To answer that, let's have another look at our loss function. We can replace f with w because our model is just a constant. Now, if we plot the values of the loss with the different values of w, we'll get something like this. So ideally, we want to find the lowest point of the loss function. It turns out the optimal value for this particular error function is actually the median. For this particular choice of loss function and model, we can prove that the median is the optimal solution. But instead of discussing the proof which only works for this example, I want to talk about a more general solution that not only works here, but also works on much more complex models that we'll discuss later, and that is using gradient descent. The idea of gradient descent comes from the observation that if you start from a random point on the loss surface and compare the loss slightly to the right with our current location, if this difference is negative, it means that loss is falling. So to find the minimum, we need to go to the right. If the difference is positive, on the other hand, we should go left instead. Now we can keep iterating this process until we find a good solution. Note though, if we take too large of a step, we may miss the optimal solution and end up oscillating around the optimum. So we want the step that we are taking to be small. We often normalize this difference by the size of the step to make sure this number doesn't become too small as we decrease the step size. Now, we can actually make the step infinitely small. In the limit, this ratio is referred to as the derivative of L with respect to W. If W is multidimensional, we can compute a vector consisting of all of the derivatives with respect to each dimension of W. This vector is called the gradient of L with respect to W. At each point on a function, the gradient vector points to the direction that the function is most rapidly increasing. The gradient is a very important and well understood part of vector calculus, and we know how to derive the gradient of a large category of functions. These functions are called differentiable functions. Libraries like PyTorch or TensorFlow can automatically compute the gradient of a given function for us. At the heart of the gradient descent algorithm is an update rule. The update rule says that at each step, we should move the weights towards the negative direction of the gradient vector. Note that we introduced an extra parameter, alpha. This is called the learning rate. The reason we introduced this new parameter is to control how fast we are traversing the loss landscape. The learning rate is one of the most important hyperparameters when training a neural network model. The best value for the learning rate depends on the problem and can be experimentally found by trial and error. Okay, so let's review the gradient descent algorithm. We start with an initial guess of the model parameters, which could be just random. We compute the gradient of the loss function with respect to the parameters and move to the negative direction of the gradient. And we repeat this process multiple times until we reach a point where the update is near zero. Let's try what we have learned in code. We're going to use the Python programming language along with the PyTorch library here because these are the most popular choices for machine learning experiments. First, we import the Torch library and define our training inputs and targets as two tensors. A tensor in PyTorch is simply a multidimensional array. Each row in our tensor X consists of 4 dimensions. The first dimension is the size of the house in square feet, and the second dimension is the number of rooms, and the third and fourth dimensions specify the location of the house. Each row in our target tensor has just one dimension, which is the price of the house. Now, before trying to use this data to build our machine learning model, I want to mention a very crucial step in implementing machine learning algorithms, and that's data preprocessing. You see, in mathematics, numbers are exact, so we can use arbitrary units to represent any property. Numbers on a computer, however, have a fixed precision, and the units in which we represent our data can greatly affect the precision of our computations. This is one of the reasons we usually normalize our data as the first step. A common normalization method, which we apply to our inputs here, is to subtract the mean and divide by the standard deviation. This ensures our inputs follow the standard normal distribution. For the targets, our original data was in $1,000 units, so we divide everything by 1,000. This way, most prices are between 0 to 1 range. Generally, keeping most of our data close to -1 to 1 range is a good practice when doing any numerical computation. Okay, now let's see how we can train our first model. We start by importing the Torch module. We define W as a parameter and initialize it with a random value. we define an instance of the SGD optimizer class which implements the gradient update rule. The optimizer takes the model parameter and the learning rate as arguments. Then, for 1000 training steps, we repeat the following. We define the loss function as the average absolute difference of our parameter W and price targets. Behind the scenes, PyTorch allocates an extra buffer to hold the gradient vectors for our parameter, and it keeps track of the dependency of our loss function to the parameter. The next 3 lines apply the gradient update rule. The syntax might be a bit cryptic, but what we are essentially doing here is that we set the buffers holding the gradient vectors to 0. Next, we compute the gradient vectors and populate the buffers. And lastly, we update the parameters according to the gradient update rule. If we run this code and visualize the value of the loss with respect to our model parameter, this is what we get. You can see that starting from a random guess, gradient descent gradually improves our model prediction error until it converges close to the optimal point. But notice how gradient descent is so painfully slow. Gradient descent rapidly decreases the error when the loss surface is steep, but it grinds to a halt in flatter areas. But there is a simple way that we can resolve this issue to a large extent. The idea is, if we are moving in a direction and the loss is decreasing, we should just keep moving in that direction. So instead of solely making the updates based on the gradient vector at the current location, we can also take the previous update vector into account. This way, if the gradient vectors are in the same direction, the optimization accelerates. And if the gradient vectors are in the opposite directions, the optimization decelerates. This technique is referred to as momentum. PyTorch already has a built-in implementation of momentum in its SGD optimizer class. So to implement momentum, simply set the momentum argument to a value greater than 0. We set it to 0.9 here. Let's see how this works in practice compared to vanilla gradient descent algorithm. It looks significantly improved, but there's more we can do. Recall that in gradient descent, parameter updates are calculated based on the gradient of the loss function, where the loss value is computed based on the whole training dataset. It turns out we don't really need to compute the loss over the whole data, and it's enough to just use a random subset of the data at each step. This way, we don't need to do as much computation as we needed to do before, which significantly increases the training speed, especially when our training dataset is large. This algorithm is commonly referred to as a stochastic gradient descent, or SGD. Let's see how to implement this in PyTorch. Most of the code is the same as before, but notice we have split our data to batches of 64 samples, and during each training step, we only use this batch to compute the gradient. Let's see how stochastic gradient descent performs when compared to gradient descent. Note both implementations here are using momentum. That's a lot faster. There's still more we can do on the optimization front, but SGD with momentum is a great baseline which, if tuned properly, often can perform as well as any other method. But let's switch gears to improving our model instead. Now, we have discussed using a constant model to predict the price of houses, but of course in reality house prices depend on a number of factors like location, size, number of rooms, and etc. Let's take those factors into account. Let's add an extra term to our model for the size of the house in square feet. Note that x1 here represents the size of the house, and w1 is an unknown coefficient that determines how much the size of a house contributes to its price. So this model is not a constant anymore. The predicted price f of x varies based on the given house size x1. We can add another term for the number of the rooms. We add 2 additional parameters for the location of the house, one for the longitude and another for the latitude. We can rewrite our model in vector format as f of x equal w transpose x. Now, this model is called a linear model. Our linear model has 5 dimensions, so it actually represents a hyperplane in a 5-dimensional space. This model can also be seen as a neural network with just one weight layer. A weight layer is also known as a hidden layer since the parameter values are initially unknown. Note that with 5 parameters, the search space to find the optimal parameter values is vastly larger than the constant model we explored before. In fact, the search space is exponentially expanding with increasing the number of parameters. This phenomenon is known as the curse of dimensionality. Fortunately for us, the gradient descent algorithm works well with linear models of any size. Let's implement this in PyTorch. We use the built-in linear model in PyTorch and specify 4 dimensions for the inputs to the model and 1 dimension for the output. We use the stochastic gradient descent algorithm to optimize the parameters of our model as before. Okay, so let's run this code and see how it compares with our constant model. That's a lot better. Note, both of the models converge after a number of steps, but the linear model converges to a much lower prediction error. The linear price predictor model performs pretty well, but the prediction error is not zero. In fact, the error is not zero even on the training set, which suggests that perhaps the relation between a house's attributes and its price in our dataset is not linear. We can always use a linear model to approximate a nonlinear function, but this approximation is never going to be perfect because a linear model cannot represent a nonlinear function. Let's try to understand why. Assume we are trying to build a model that determines if a given point is inside a circle or not. This is an example of a nonlinear model. Now, let's consider a linear model of the form h equals w transpose x. We can use this linear model to cut the space in half depending on whether h is positive or negative. So our model considers a point to be inside the circle if h is positive and outside the circle otherwise. Now, of course, our initial parameters are quite bad, so let's adjust them. That's still pretty bad, and we can't really do any better with a linear model. But what if we introduce another linear model? Can we somehow combine the two models to build a more accurate model? Let's try adding the two models and see what happens. Well, if we just add the two models, we'll just get another linear model. And it's easy to see that because we can factor x out of our equation and sum the weight vectors to get another weight vector. This again represents a linear model, so that doesn't really work. So what can we do to solve this problem? One way to solve this problem is by using an activation function. Activation functions are simple nonlinear functions that can be combined with linear models to create more complex models. One such activation function is a step function. The step function has 2 values. For all inputs x less or equal to 0, it produces 0, and for anything else, it produces 1. Let's get back to our linear model. Now, if we add a step function on top of our linear model, we can see that it simply partitions the space into 2 regions. On one side, the model outputs 0, and on the other side, it outputs 1. But if we add 2 models with the step functions, we see something interesting. The combined model partitions the space into 3 regions with values of 0, 1, and 2. Let's add another component and another component. Note that with just 4 components, we can distinguish points inside a square from the outside. In fact, we can keep adding more and more components to the point that our approximation of the circle becomes very accurate. That's great, so we can combine linear models with activation functions to form more complex functions. There's, however, one problem, and it has to do with the shape of the step function. Notice the step function is quite flat, so the derivative of the step function is 0 everywhere except at 0, where it's undefined. So if we try to use gradient descent to optimize our model parameters, gradient descent would simply get stuck, as it can't tell in which direction the loss decreases. So the step function is not a good choice. A very popular choice for an activation function is the rectified linear function or the ReLU function. Note that ReLU is just the identity for all positive numbers and 0 everywhere else. So the derivative is 1 for all positive inputs and 0 for non-positive numbers. That still seems not ideal for gradient descent, as the derivative is 0 in half of the space. But it turns out in practice, if we initialize our model parameters carefully, gradient descent can perform pretty well with ReLU. Okay, there's one more thing that I want to talk about before moving to implementation. Let's have another look at our model. Say our model is the sum of 3 components, with each component composed of a linear model and an activation function. Let's rewrite the sum as a multiplication of a vector of 1s with a vector h1, h2, h3. Now, this model can also be seen as a neural network with 2 layers. The first layer has 3 components, but the second layer consists of a vector of 1s. But the second layer doesn't have to be just 1s. It can be another weight vector. Such a model is often called a multi-layer perceptron or an MLP. In fact, an MLP can have an arbitrary number of layers. Okay, now let's see how we can implement a simple MLP in PyTorch. The main change from our previous code is the definition of a new class that we call MLP, which encapsulates our entire model. In the constructor, the MLP class takes the number of inputs dimensions, hidden dimensions, and output dimensions as arguments. We then define 2 linear layers, the first mapping the inputs to an arbitrary hidden space, and another layer mapping this arbitrary space to the output space. Note that Torch requires all our model parameters to be defined in the module constructor, and that's what we did here. The forward function defines the operation that the model does on its inputs. So it takes the inputs x as arguments, applies the first linear model, followed by a ReLU activation function, and then applies another linear layer on the result. The rest of the code just implements stochastic gradient descent optimization to find the optimal parameters of our model as before. Let's see how it all works in action. We can see that the multi-layer perceptron performs slightly better than the linear model. It may be possible to tune this model to get better results, but because of some inherent noise in our data, we can't hope to get 0 error in this problem. So we declare a mission accomplished for our house price prediction model and move on. And that is the essence of machine learning. While there's still more to cover, the technology behind the latest image generation, chatbots, and autonomous robotic systems all boil down to training deep neural network models that approximate functions. Functions that map random noise to a realistic image. Functions that predict the next word given the previous words. Or functions that determine the best next action to take given the current state of the world. If you're as excited as I am to learn and experiment more with this powerful technology, make sure to subscribe and leave in the comment section with your questions or requests for any topics that you want to see covered in future videos. So until next time, take care.